Welcome everyone to the Digital Finance seminar series today. This is our second seminar of the semester. We have 3 more seminars coming up. Just to advertise the immediate next one, it's going to be a week from today in the same place. And that's going to be on the topic of zero-knowledge proofs and proof of solvency and proof of resiliency. However, today our speaker is Matt Weinberg. Matt is an assistant professor of computer science at Princeton University. His area of expertise is algorithmic game theory broadly, and more specifically, he's done a lot of work on blockchain protocols, which he's going to tell us about today. Thank you, Matt.
Awesome, thank you. And thanks for having me here. So I'm going to talk, this is going to be a little bit more of a survey talk. So you can see this is several papers over a long period of time that I'm going to mention. And the first chunk of the talk is also just going to be background. So I will try to read the room to get a sense of whether any of the background I'm presenting is redundant. But anyway, I will get started. So the theme of this talk is basically the following. So blockchain protocols, I think, are really just mechanisms from the econ view of mechanism design in the following sense, that all of these protocols provide actions that they would like participants to take. They clearly specify payments as a function of the actions that everyone takes. And they also specify desired behavior that they would like the players to take. So the non-mechanism design view is they would say the protocol is what they tell everyone to do. But I think the mechanism design view is that really they're setting up a game, and they are also proposing behavior that they would like everyone to be incentivized to take. And so, before maybe 7 or 8 years ago, when I was just starting into this, it was not common to think about this from a mechanism design perspective. And the common view is a classical security view, which is that you say, well, what if some fraction of the players are honest? Can I guarantee that if at least 51% of the players are following the protocol, or at least 66% of the players are following the protocol, then I get a desirable property. And this would be even if the remaining players have no incentives whatsoever, they're just out to destroy you, then you would still like something desirable to happen. So in that sense, it's stronger than mechanism design guarantees, but in another sense, it's weaker because you should ask, why would you get an X fraction of the players to be honest if they're incentivized to do something else? So what I want to do in this talk is I'm going to overview several models that I would claim capture the underlying incentives in various blockchain protocols. There's a question mark here because depending on how many questions there are, I may not get through more than one model, which is fine. And I'm totally happy to just pause as long as necessary for whatever people want to discuss. But if things go smoothly, then I'll go through a couple different settings. And what I would like to give, the biggest thing I hope to get away is I would like to give intuition for why manipulation is often profitable in these settings. So I hope that I will also get to state a lot of results. But if I don't get to do that, but I instead get to pass on that intuition, I think that's what I'm primarily focused on. Okay, so what are the themes that are going to come up? So all of these protocols, they will eventually have some claim of the following form, and they previously have made some claims, maybe not in a formal sense like this, but they used to operate in the following form. They would say, it's a Nash equilibrium for everyone to follow the protocol as long as nobody is too big. So for example, even in Nakamoto's original white paper, he was aware of a 51% attack on Bitcoin. And so he knew that they knew that if there was a single player that had more than 51% of the computational power, that would be a problem. And however, since then till roughly 2014, everyone kind of largely assumed that 50% was the right threshold. And then there was a seminal paper that kind of kicked off the discussion that it was not the right threshold. And then there's been a lot of work since then. So what I'm going to show you, I think the most interesting divide is between protocols where this number X is bigger than 0. So the right interpretation of that is these are protocols where as long as no player is sufficiently large, then following the protocol does form a Nash equilibrium. Okay, so that's some class of protocols. The 2 that I'll go over are basically if you have some understanding of how Bitcoin works, that holds in Bitcoin. There's a variation that I'll define when we get there, which I would call proof of stake longest chain. If you have external randomness, if you don't know what those words mean, that's fine. And in some cases, X is 0. So what that means is that the way these protocols are designed, anyone can strictly profit by deviating, even very small players. And so to me, this is what I think of as the most interesting divide. Again, everything I'm doing is in stylized models. I'm not like coding up attacks you can actually use. But I think from like what do we learn from theory, to me, this is what I think of as like one of the more interesting divides, is do you need to be large to strictly profit, or can anyone do it no matter how small? And so I'll go over what all these terms mean later, but if you know what these are, then these are the settings. Okay, so what I would like to do now is I would like to just dive straight in to kind of the canonical classic setting, which is like Bitcoin proof of work with a block reward. So I am going to give a quick overview of what I think are the salient factors of Bitcoin's consensus protocol. If you already know it, then the next couple slides will be repetition. But if you don't, I hope this will capture just the necessary bits. So okay, so there's text up here with a kind of formal definition of what is a hash function. The main thing I think you need to take away is just what's on this last bullet. If you haven't seen a hash function before or you haven't thought about it a lot, it's a random function in the sense that if you give it a new input for the first time, you get a uniformly random number. If you give it an input you've already given it before, you get the same output. So it's consistent, but if you haven't queried it before, you get a random number. And in a nutshell, like what's going on with Bitcoin, they have this protocol that lets you prove work to create a block. And they say every time you create a block of new transactions, what should you have? You should say, well, this is the person who's creating it. These are the transactions you want to authorize. You need to say, like, what's the history you're appending to? And then there's this thing they call a nonce, which has no semantic meaning. And the only purpose of the nonce is to have this. So the idea is that this concept of proof of work says that, like, if somehow you can find some input to a hash function that is extremely small, so remember this is a random 256-bit number every time you query it, and if somehow you get something that has 70 leading zeros, this is a 2 to the minus 70 event, then this is considered a valid block, and now you can add that, people will recognize that, and stuff like this. So this is kind of like all you need to know about the Bitcoin protocol for what I'm going to discuss. And then if you've heard this phrase mining just refers to you repeatedly guess nonce over and over and over again. So you try 0, you try 1, you try random numbers, whatever you're doing. And the idea is that, if h is really a uniformly random function, then there's no faster way to find a valid block than just to update this and guess again, right? That you can that there's no, or that's the assumption. Now in practice, h is not a uniformly random function, it's a hash function, but the idea is that something like this is the formal property you would want to say that really the best thing you can do is just randomly guess. Okay, so at all points in time, Bitcoin has this blockchain that looks something like this, and I've highlighted this red one. I'll mention later this thing called the longest chain, which you can tell by this picture just has the longest path coming out of it. Okay, so the point is that when you are mining, so when you are going through this process, the idea is you are iterating through nonces because they have no semantic meaning. You as the miner, you get to choose all of these. Now, the obvious thing to do is you should use your own public key because this is how you collect your rewards for creating a block. These two are entirely up to you. And the game is that you should set those to maximize your rewards. Okay, so these are the things you can strategically decide. You can decide where you want to point. So like this block could have pointed here, could have pointed here, could have pointed here, could have pointed here. And I'm not focusing on the transactions right now, but you can include whatever set of transactions you want. And the other thing that is not obvious is you also can decide when you want to tell other people about this block you created, right? So you have all this hardware, you're mining, you're guessing, and you created something that successfully proves work. Like you can just hang on to it for a bit before you broadcast. You're allowed to do that. Or you can broadcast it immediately. And what the Bitcoin protocol asks everyone to do is just to include everything that's valid that hasn't been included already in what you're pointing to. They would like you to point to this longest chain, which is, in this picture, the red is the unique longest chain. If the red one wasn't there, they would ask you to pick one of these two and to tie break in favor of whichever you heard about first. And they would also ask you to just broadcast immediately. That delaying your broadcast runs the risk of conflicts. That's not good for the network. Okay. And if everyone is following the protocol, or sorry, even if everyone's not following the protocol, the observation is that the miner of the next block is selected proportional to their rate of being able to hash. That's called their hash rate. And this is random and it's independent of all previous miners because really there's nothing fancy going on. Everyone's just trying to guess random numbers as fast as they can until they get a small one. Okay, and then the last piece of the puzzle is that everyone gets, why is everyone doing this? This is because you create a new Bitcoin when you create a block. And what I want to highlight, just in case you haven't seen it before, is that this reward that you get for creating a block, it's not like someone pays you US dollars and say, I recognize that you've created a block, here's some US dollars, thank you for doing so. What you get to do is when you create a block, there is an implicit transaction in your block that gives you 6.25 new Bitcoin. So what that means is that in this picture, D and A, they did create blocks, they spent computational power doing that, but in the ledger defined by C, they do not have 6.25 Bitcoin for doing so. So you get rewarded only if your blocks make it into this longest chain because this is the ledger that everyone believes. Okay, the very last piece of the puzzle, and then I will pause in case there are questions about this and then give you a model, is this target I said on the previous slide was about something like this. This is ballparked. I think this is roughly accurate, but it's somewhere around here. And this target dynamically adapts over time. So what the protocol designers decided is that, this target of having 70 leading zeros, that's not really going to be universal throughout time. We may get, better, and that's not an objective thing that makes sense to me. But they said the concept of a block being authorized every 10 minutes, that's a concept that makes sense to me that may be, universal-ish throughout time. So they said that's what we want to be invariant. I want it to take 10 blocks in expectation, or 10 minutes in expectation to create a new block. And so what this means is that that's the invariant. The difficulty will adjust. So what that means is if I really want to think through what is a miner's kind of over time average reward for participating in this protocol. So the important thing is that they definitely need to put blocks in the longest chain. Just creating blocks alone is not enough. They need to be in the longest chain. And the other thing is that, well, if the longest chain is length t, that means that 10 t minutes have passed because of the difficulty adjustment. So I would say what I really care about is like my reward per unit time. And so what this really means is that my time average reward is proportional to the fraction of blocks that I create on the longest chain. So just to think through that a little bit before getting into the model, it does mean that it is better for me to have created 9 out of 10 blocks in the longest chain, because that means that I created 9 blocks in 100 minutes versus 10 blocks out of 20, because that means that I created 10 blocks in 200 minutes. And when I care about the rate at which I'm accumulating profit, the rate is faster for 9 blocks out of 10 versus 10 blocks out of 20. Okay. So let me pause here in case so I've skipped a lot of the crypto details of the Bitcoin protocol, but I just want to focus on the consensus aspect and the incentives. So all I've said so far is that you have the freedom to set the transactions however you want, point however you like, choose when to broadcast. And I'm, for the first part of the talk, ignoring fees. I'm just saying you get rewarded 6.25 Bitcoin per block in the longest chain, and that your reward over time is exactly proportional to the fraction of the blocks in the longest chain created by you. So I'll pause in case there's questions about this overview part. Yes?
So I apologize if this is pretty basic.
That's okay.
But in terms of the properties the hash function needs to have, does it need to satisfy certain properties like belonging to a universal hash family or like KY's independence or something like that flavor?
Yeah, so it does not, I would say likely whatever hash function you're using should, let me go back. So those properties are ones that I would say theoretical computer scientists use when we talk about like drawing a hash function from a distribution.
Right.
So in this case, there is a single hash function used in practice. So that's SHA-256. So there's kind of like no sense in which a single hash function could be 2 independent.
Right,
Because there's no more randomness.
Right.
So SHA-256, sort of a single function, doesn't have properties like that. However, you can think through sort of like what does it mean in practice? Like in practice, what we're hoping is that all the things that you might do to a hash function that was drawn from a distribution that was not 2 independent, you can't do those computationally efficiently to SHA-256. Okay, now of course the code is there, and there is a well-defined answer to what is h of x. But like the hope is that whatever you would want to do with that, you can't do anything more efficient than just, querying SHA-256 on x. Does that kind of?
Yes, it does.
Okay.
Thank you.
So the main thing I would say is that we probably don't want to focus on formal properties of a single hash function, but definitely you want it to be the case that like we really don't believe you can abuse SHA-256 and do anything other than just query it on inputs and see what you get.
Thank you.
Yeah. I forget, was there another? Yeah.
Do you consider halving your model?
No. So the question was whether we consider having, so over time, the block reward will have. So I would think of this as just saying like over a 4-year period. So the block reward is stable over a 4-year period. So think of it as sort of like on that kind of scale. I'm not thinking about like a 20-year long deviation or something like that. That being said, like the only difference would be that would make you have, if I wanted to bring halving into the model, it means that I would have higher priority for blocks built over the next 4 years than blocks built 4+ years from now. And all the scale of the deviations we're going to talk about are like way shorter than 4 years. So really the right thing to do would just be like do them now and also do them 4 years from now, and they would still be profitable. Yeah.
So I'm just trying to understand what would happen if, right, at some point I'm on the longest chain, and then I get rewarded based on the average number of blocks that are mined over this period of time. Then at some point somebody makes an attack, so it forks the chain, and I'm no longer on the longest chain, but I've already received my
Great question.
reward and I might have used it. So is there a way to?
Yeah, great question. So the models I'll talk about today are not considering stuff like that. So the models I'm talking about today, let me answer that in like 2 slides. There'll be something on the slide that's kind of related, but basically what I'm going to say is that I will give more power to the protocol in the sense that I will not let attackers benefit by getting profit and then losing it, but they already cashed out for USD. So attackers in this model will only profit if their profit stays on the longest chain forever. Okay. All right, so very quick, another quick recap is that there's a lot of things that are very naturally defended against just by cryptography. So digital signatures are great. That means that I can't pretend to be someone else and just spend their money. Also, I didn't get into this, but like you might worry about like, oh, I made a block and I said I was pointing to this, but now I'm going to retroactively pretend I actually pointed to this, or I pretend that the transactions are different. That's actually well defended against by hash functions. So just the fact that you point to blocks by their hash, if I change the content of the blocks, the hash is going to be completely different, and then now everyone's going to know that I changed something about the content. Like one of the big things that's talked about with blockchains is that they're censorship resistant because anyone can mine a block, so that even if I'm mining 99.9% of the blocks, that 0.1% of the blocks, someone else can include a transaction that I chose not to. So cryptography is great and solves all these problems immediately. And just to repeat, I'm going to hit this point a couple times, is that you can point to any block you want. There is no way cryptography is going to solve that problem, right? And you can include any set of transactions you want. There is also no way cryptography is going to solve that problem. And you can broadcast your block whenever you want. these are not cryptographic problems. These are incentive questions, right? There's no way to get around those with just cryptography. Okay, so now I'm going to give you an example of a stylized game, and I'm going to go through this one in a little bit of detail. It's going to fit on one slide. Later ones I may go through in a little bit less detail, but just to give you a sense that like the models are not super complicated, but I do think they capture what's really going on. So here's the setup. Every miner in the system has hash power, and let's say that's fixed. So this is again simplifying the model. I'm not considering that an attacker may profit now, then go buy more hash power, and then profit more later. I just want to look at, even if everything is fixed, what can the attacker do? And at all points in time, miner M is aware of all the nodes that like they have personally created and all the nodes that have been broadcast by others. And you know, if you kind of remember this picture I drew, for this game, really all that matters is where things are pointing. So I'll just call it a graph. I don't really care about the transactions inside because I've decided that I'm not counting the fees for now. So really just think of it as a graph, and you have every time you create a new node, there's a directed edge. Okay, so how does the game evolve? So initially, everything is empty. And then every time step, there's a random miner selected to create a block. And they're selected proportional to their computational power. And what does it mean when you're selected to create a block? You create your block, and as you create it, you have to decide where you point. Now, the reason you have to decide at the moment of creation is that this was in the thing that you were trying to hash. So as you succeeded, you had to know where you were pointing before you knew that you were going to succeed. You can't change this later. And every time step, after someone creates their block, all the other miners, including you, are allowed to broadcast whatever you want. I have a very simplified model of broadcasting is just when you broadcast, everyone hears about it. Okay, so again, I'm not giving the attacker the power to like selectively broadcast to some nodes but not others. That I really want to capture rewards that the attacker can get just by manipulating the consensus protocol, not by manipulating the network, not by investing in more power and stuff like this. Okay, and then as I mentioned before, I want to say that the payoff, this is your time average reward, is just a steady state fraction of blocks created by you in the longest chain. So if you, maybe I'm not going to read through this math, but I just put this up there just to promise you, you know, if you are careful, you can define it so that it's, you know, here. Maybe the only tricky step here is related to the question that came up earlier of like, what if the longest chain is changing over time? So I'll take away all that power from the attacker. I'll say that like if somehow there's like something funny going on and the longest chain is always changing, then everyone gets 0 reward. That you only get reward if there really is like a stable longest chain over time, and for every block at some point you can say it's in the longest chain forever. Okay, so I really want to only consider a very restricted kinds of attacks that just come from creating more blocks than you're supposed to be. Okay. Let me also take a quick pause just to see if there are any questions here. I am going to go through some, you know, like images of how this game might evolve, but yeah.
M is a miner and T is a time step.
Correct.
Then what is G of M and G of T?
Yes, so G of M, I'm just referring to, this is the set of nodes that miner M is aware of. So how this will always be, these are the nodes that M created themselves, or nodes that have been broadcast by others.
To M.
So broadcast means broadcast to everyone, correct. So the broadcasting is very simple in this model. So maybe just to repeat this part, the idea is that when you are mining, you are definitely aware of every block you have previously created, and you are aware of every block that anyone else has broadcast.
There's no delay in the broadcast.
There's 0 delay, that's correct. Yeah, so all of that, I want to take all that power away from the attacker. That all they can do is be clever with how they point, they can be clever with when they broadcast, that's it.
What's the sense of steady state here?
Yeah, so basically what I mean here is that like, I'm imagining that like say you want, you know, you've decided you're going to become a Bitcoin miner and you're going to do it for about a year. And then I want to ask, how are you going to make the most money over a year? And so I would say the way you make the most money over a year is you maximize your payoff in this game. I think that's what I'm trying to capture. So I don't want to like, I don't want to like maximize my reward specifically tomorrow or specifically 2 days from now or over like a 10-minute window. I want to maximize the reward over a long period of time. So maybe let me say the steady state is basically exactly this. So this is like the limit as time goes to infinity of the number of blocks you have in the longest chain over the length of the longest. Sorry, maybe that, sorry, I answered the non-technical one. The technical one is, yeah.
So maybe like long run average, not so much steady state.
Sure, yeah. Yeah, yes. It will happen to be the case that there is a Markov chain that describes all the strategies we're considering, so there will be a steady state, but I should not take for granted that other strategies would have that. Okay. All right, so let's quickly go through. So in this language, I've simplified a lot of stuff. So we can say, what is the Bitcoin protocol asking you to do? So they're asking you to do, so remember there's two things you have to decide, is where do you point and when do you broadcast? So they say you should point to the longest chain. So that's the furthest node from the root. And you should, it's not super important how you break ties, but it's safest if you break ties in favor of whatever was broadcast earliest. And if there were two broadcasts in the same round, just break the ties randomly. And you should always broadcast everything. They just broadcast immediately. Don't hide anything.
Why do you break ties in that way? I mean, if you have more nodes in one chain, which has the same length as another, you have more gain. You gain more from.
Yeah, good question. So there are fancier tie-breaking rules that have been proposed. The one that Bitcoin, so my understanding is that what is considered the Bitcoin protocol is point to a longest chain. And they say if there's a tie, they don't say it's part of the protocol for how to break the tie. However, what is typically encouraged and done in practice is just say whichever block you heard about first, among those that are the same length, that's the one you should break ties in favor of.
This is a protocol. You're not talking about your strategic.
Yes, that's correct. Yes, that's correct. So there's no strategy yet. This is just what Bitcoin asks everyone to do. And okay, so now I would say, so here is, again, before game theorists got involved, people in the blockchain community were not using formal language like Nash equilibria, but I think it's reasonable to say that if you took claims that were being made and tried to put them in a formal language, it would have sounded like this. So it would have sounded like, if all the other miners follow the longest chain protocol, and you have less than 50% of the computational power in the network, then your best response is to also follow the longest chain protocol. And there's some argument that's even in the original Bitcoin white paper for why this is the case. And so Nakamoto considers well, here's one deviation you might try. You might try to just make your own chain and just say you ignore what everyone else is doing and you just make one on your own. And then if you've done any random walk analysis, Nakamoto actually did that in his white paper, they showed that, well, if you're finding blocks at a slower rate than these guys and you just have two separate chains, you will always eventually lose. And so they said, well, so that is one attack that will only work if you have more than 50%, and this will not work with less than 50%. And so this was kind of accepted for a while as the right cutoff. And then, this is the paper that got me very interested in the space. There's this really cool work that showed that actually there was something more clever you can do. And so this is now colloquially referred to as selfish mining. And they showed that actually if you only have a third of the computational power, then there is something better you can do than following longest chain, even when everyone else is doing it. And so that kind of lowered the threshold from a half to a third. And let me now go into a little bit of detail with this. And so this is the part that I'm hoping people actually get some intuition for what's going on. And if this winds up taking up the rest of the talk and I don't get to say anything else, that's okay with me. Okay. So let me give you some intuition first for how this could possibly work. So let's imagine, so this is not capturing practice. Let's imagine that somehow all of the other miners, they've decided to tie break in favor of you. So I don't know how they would decide to do that, why they would decide to do that, how they would even recognize which blocks are created by you or others. Let's say somehow that is happening. Okay, so they are still following the longest chain protocol. The only difference is they break ties in favor of you. So now what can you do to be a little bit more clever? So here's what I would do. I'd say like, well, the good news is that I'm in no rush to publish my blocks, because even if I wait a little bit and there's a competitor, then I'm going to win the ties anyway. And that's actually good for me to cause conflict that I win, because now there's fewer total blocks in the longest chain, because I've now knocked out this one that I was conflicted with. And as long as all of my blocks are still winning and in the longest chain, I now have a higher fraction. So here's how I would describe that strategy, is just, I followed the longest chain and tie break in favor of myself. The only difference is I'm not going to rush to announce my blocks. I'm going to wait until there's competition, and then when there's competition, I will broadcast. Okay, so let me just show a picture of what this looks like. So here in the blue, so I'm changing blocks from red to blue when they've been broadcast, and this means that it's found by not the attacker, and there'll be an LSM if they're found by the attacker. So some honest player finds a block first. Great. And then I find a block, I point to the longest chain, and I don't broadcast it yet. And now someone else finds a block. And I say, okay, I heard about this block, so now I'm going to broadcast mine. And then I find another block. I'll, of course, point to mine and say there's, another conflict. I say, great. And now the good news is, because everyone breaks ties in favor of me, that even if I don't find the next block, that I'm still going to have all of mine be in the longest chain. And the good news is that the longest chain is shorter. It's only 4. So I get half the total rewards here, whereas if I were honest, I would have gotten a third, because it would have been 2 out of 6. Okay? And you can do some quick math and see that basically, well, let's not worry about the math, but the point is that you do strictly better than honest, no matter what your hash rate is. Give me 1 second. And then, but I want to say this really relied on them tie breaking in favor of you. Yeah.
I'm just going to follow up on the point that there's fewer blocks in the thing. If somehow you got everyone else to produce blocks off the wrong chain, the difficulty adjustment would take a while to kick in, right? So there wouldn't be you would also be slower in generating blocks, right?
Yes. Okay, so the question is about so how long, exactly. So the question is, how long does it take for the difficulty adjustment to kick in? So that is a 2-week horizon. So the idea is, if you want to maximize your profits for the next 2 weeks, this attack is not helping at all. If you have a 2-week deadline to do something, the difficulty adjustment will not even change. The difficulty adjustment is set. You just want to make as many blocks as you can in the longest chain. That's it. If your horizon is, I'm imagining, like several months, then the difficulty adjustment will kick in after 2 weeks. Now you're maintaining the same steady state. So the difficulty will stay the same for the next forever. But for the first 2 weeks, the analysis is not correct. As soon as you pass the first 2 weeks, then the analysis is correct. Yeah.
So the computing power matters because the rate at which you can create yours
Exactly.
need to be fast enough.
Exactly. That's correct. Okay. So this is, I hope, get some of the intuition, which is that by intentionally creating conflict, you can get more reward so certainly if you win all of the conflicts, then this is good for you. Okay, but in order to win all of the conflicts, I really needed everyone to tie break in favor of me. But that's the intuition for what's going on, and now I'm going to show you, a different attack that requires a little bit of math to analyze. Yeah.
Yeah, sorry, I was curious by how much is the chain gonna be actually shorter? Because if I will broadcast as soon as somebody else broadcasts, then it doesn't seem like the chain is gonna be a lot shorter.
So it's going to be shorter by exactly your hash rate. So if you produce a third of the blocks, you are also canceling a third of the blocks. And so all of a sudden, the effective hash rate has gone down actually by a lot. Because now basically a third of the blocks that used to contribute are now just disappeared. Yeah. Okay. So now let me give the actual strategy that works. So I'll state the strategy here, and then I'll go through some pictures. The pictures will explain why it works. So I'm still always pointing to a longest chain. I still tie break in favor of myself. So these are kind of like the no-brainer things to do. Now what I'm going to do is the following. I'm going to be creative when I broadcast, where certainly I will broadcast as soon as there's a challenger. So this is the same as before. Now what I'm going to do is I'm also going to say, look, if I have this pivotal block that points to something that's in conflict, and I don't have anything else to keep this block safe, then I really just want to like rush and publish it because I'm the only one who I can count on to tie break in favor of me. So let me go through this in a picture. Okay, so I'll start by someone else finds a block. Great. Remember, they're tie breaking against me now. I find a block and I'm going to hide it. Okay, so I'm going to hide it because it doesn't pass any of these, so it's not pivotal. We'll see what pivotal means in the picture, and there's no competition. Okay, now I find a second block, and I hide it again. Because again, there's no competition, and it's not pivotal. Then I find a third block, and I hide it again. So at this point, I would like to point out, like, this is great in the sense that, like, I have 3 private blocks that the rest of the network doesn't know about. So, like, in particular, even if they happen to find 2 in a row, I still have 3, and even if they tie break against me, it doesn't matter because 3 is more than 2. Okay, and so that's what will happen. So they have, so they find a block, and now this one has competition, so I'll broadcast it. Say, okay, cool. And then they find another block, and now this one has competition, so I broadcast it. And now I look at this picture, and I'm like, okay, now I'm actually a little bit scared because, like, if I hide this one too, and they find the next block, then I'm going to lose all 3 of these, and that doesn't help anyone. So I'm just going to be like, okay, yes, I would love it if I could kick out 3 blocks with my 3 hidden blocks, but I'm really nervous about that. So I'm just going to broadcast this, and now everyone's going to point to mine because I'm the unique longest chain at this point. Okay, so this is what I'm hoping will happen. Okay, so now there's a risk, which is different than when everyone tie breaks in favor of me. Okay, so this is the interesting case. So I hide my block. I don't yet have a safe one when there's a competitor. So I broadcast this. And so this is where good news for me is I still find the next block, and then I just immediately publish it, and I'm just like, very thankful that I got this in the longest chain. I kicked this out. That's exciting. The bad news for me is if I don't find the next one. If I don't find the next one, then they tie break against me. I lose this. So there's an actual cost. And so that's basically the trade-off. Okay, so it's not risk-free anymore, but the idea is that, you can try to do some analysis and see, like, what's the probability that you wind up in a good case versus a bad case? How much profit do you get when you're in a good case and how much you lose when you're in a bad case? And it turns out that, these guys did the math. Yeah.
Why did you publish the first block? So go back,
Here.
why did you publish there? Why not wait?
Yeah. Great question. So I would say it is neither helpful, it would be totally fine to hide it, but it neither helps nor hurts me to hide it. So for example, if I did hide it, so pretend it's hidden, then I would still want to publish both of these. At this point, I'm fine hiding it too, because I already lost anyway. So that would be fine. The reason I typically present the attack like this way is it like, if I instead phrase this like hide all your blocks, and then all of a sudden dump 3 blocks out of nowhere, that like a natural reaction from a practitioner would be like, come on, everyone will know if they didn't hear about anything and then all of a sudden there's 6 blocks out of nowhere. That sounds like something that's easy to respond against. Whereas like I'm not stressing too much about practice, but I just feel like this sounds a little bit nicer to do it this way. All right.
So implicit in that is that this is hard to detect?
Good, so I will talk about that in a couple slides. So I will talk about that in a couple slides. Okay, so, or maybe what I would just say at this point is that like forks do happen, or like orphans do, like the conflicts do happen. So just saying there's a conflict, something's crazy going on would be like a little bit weird, but saying that there are 6 blocks out of nowhere that nobody heard about and all of a sudden happened would strike people as weird. Okay, so I'm not going to do any of the mathematical analysis, but these guys did. And you can set up a Markov chain, and maybe if you're used to setting up Markov chains to analyze things, you can kind of see that there's a natural notion of states here, and you can kind of imagine what the recurrent state would be. Like every time there's a unique longest chain, things kind of reset. And you can analyze that, and you can see that as long as you have at least a third, then selfish mining is strictly better than longest chain. And there was follow-up work that said, okay, rather than just having a specific strategy, let's write a MDP to find the optimal solution in this Markov decision process. And they computationally solved it, and they found that as long as you have, there is something better than selfish mining, but not a whole lot better. And so the cutoff is 32.9%. If you have more than that, you can do something like selfish mining. If you have less than that, then it's best to just be honest. Okay, so I'm now gonna get into what CMAC just asked about, but before I do that, yeah.
Sorry, so is there a notion of like the time until you're gonna get competition being non-Poisson, in the sense that, like, let's say I got really lucky, the first thing I tried worked, then is there a notion that I can like hide it more profitably because I'm expecting a longer time until
So it's a really good question. So what's really it's almost amazing to me how like it almost feels like luck that proof of work is so magical, but it's memoryless, the process, right? Because if it's really a random oracle, then the idea is that at any point in time, right, you're independently likely to succeed now versus another time. And so because the whole thing is memoryless, it doesn't matter whether you succeeded earlier or later. You don't need to take that into account. Now, if I really wanted to take into account the fact that like there's a finite number of nonces, there's only but it's 2 to the 256. It's sort of like it's not actually that much more likely. Good question. Yeah.
So, do I understand correctly, both the scenarios you presented had an actual tie-break rule that doesn't exist in the protocol?
It is not. I think most people would consider it not part of the protocol. Yeah.
I mean, the ties are fine according to the protocol, right? Just keep going. And then eventually somebody will build and will have a definitive longest chain.
Correct. Sorry, so the question is, when you are the one who is settling the definitive longest chain, how do you decide among the two competing longest chains?
Right.
And so the idea is, this one that I'm claiming is like a real deviation works even if everyone is deciding against your chain, and you are the only one who will break the tie in favor of your chain, then it's still profitable. For the initial analysis I did, that I consider unrealistic because you're relying on the fact that everyone else will happen to break the tie in favor of your chain when they settle the longest chain. But it's not relying on, I would say it's, so the one I consider the real deviation is completely agnostic to the tie-breaking rule because it's like total worst case here.
You always have to be a step ahead of
Exactly, that's correct. Yes?
Is the equilibrium known if there are like 3 miners who all shared the mining?
Yeah, that's a really, I'm sure, so I know that there are papers that have tried to do simulations to look at that, and how do I put it? I think it's, let me put it this way. I would say I personally know more about the literature that sort of like tries to say something insightful about practice by doing theory in a stylized model. I don't know that the papers that have looked into equilibria when there's multiple large miners have like there are simulations, but I don't know that they've uncovered like, oh, this is the behavior you could tell a practitioner about to look out for or something like that. And I couldn't tell you off the top of my head like exactly which papers they are, but I think that is something people have tried. But there's not like a closed form that I'm aware of. Right?
Still, the results is really impressive because the strategy space must be very large, right?
Yeah. Oh, this one. Yeah. Absolutely. Absolutely. Yeah. Yes, absolutely. So this is a very nice result that like basically they have some theoretical work that like trims the MDP. So first you have to say things like, okay, you actually don't need to consider what to do when you have a super, super, super long lead. And you don't need to think about what to do when, like there are 4 blocks created by the attacker and, you are still considering trying to save your previous, so there's a lot of theoretical analysis just to trim the space, which is hard.
I guess that the decision in terms of how long you wait,
Yeah.
how long you hide, It's really very arbitrary.
Yes, I agree. So this is an impressive paper that has, in addition to, at the end, like at the very, very end of all their work, they did just kind of like run an MDP solver, but there's a lot of theoretical work to do first to figure out like how do you even set up a finite MDP so that you can solve it. That's exactly addressing the things you mentioned, yeah.
What is the strategy space?
Yeah, so it is, let me go back. So it's just in this game, I think that's going to be too far back. So basically, remember, it's just every time you are called on to create a block, you can choose where to point. And every round, if you have not yet broadcast a block, you can choose to broadcast it or not. So the strategy space is sort of like, per round, it's very small. It's just, when you mine a block, where do you point? What do you broadcast? But like over time, you know, like, right, there's like uncountably many strategies, right? Did that answer your?
So it's a sequential.
Yes, correct.
Continuous time or?
It's discrete time, yeah. All right, so I think I am almost certainly going to stay within this model, but that's okay. So here's one thing I want to discuss. So one thing that people ask me often when I give this talk, and until recently I didn't really know the answer, so I tried to spend a little bit of time at least looking up what you can find on the internet. So people ask, has anyone ever done this before? And the answer is basically, it's never been detected. Okay, so it could be that people have done it and it wasn't detected, but there's no results of detecting this even on the small cryptocurrencies. Nobody has announced a detection. And just to confirm, you know, like this is according to a reasonably thorough literature and review. I read some Reddit pages too, and I don't know how much effort has been put into detecting it, but there has not been a successful detection. However, so I probably won't get to share this, but you can, you know, maybe quickly ask me about it. There is very recently, I'm aware of one strategic deviation that was detected. It was detected on Ethereum, and that was a very cool paper that maybe we'll see how things go. Okay, so now to address CMAC's question. So how would you detect if someone was selfish mining? So just to be clear, these conflicts happen naturally. You can't just say there's a conflict, something's wrong. Like conflicts happen, they're rare, but they do happen. So here's what would happen is, if you ask me, I would say like, look, I have some model in my head of how latency works, and I don't expect latency to be like correlated with the state of the blockchain, right? Like I would just say like, I don't know, like the reason that there's a conflict is because two people happen to broadcast at this, you know, happen to find their blocks at basically the same time. Like I say, my model is that it takes a second for everyone to communicate, and sometimes people find their blocks within a second. So like that happens, that seems like an independent event. But if someone's selfish mining, that's not the pattern you're gonna see. If someone is selfish mining, you're gonna see all of a sudden there was conflict 3 times in a row, right? And that's gonna be more likely, or that's gonna happen more than it would if the conflicts were independent, just because people happen to find it within a second. So maybe let me, I think I will skip this, but I do know that a lot of people find this interesting. I'm not like a policy expert or a blockchain community expert, but I have asked people who are about this, and this is my understanding. This is like what I've heard other people say. The thing I want to zero in on is that something people always say, which I think is a good argument, is that if an attack on Bitcoin or Ethereum is statistically detectable, so even if I don't know who's doing it, I can't freeze their coins. I can't throw them in jail because I don't know who's doing it. But like everyone will know that someone is doing something negative to Bitcoin or Ethereum, I might be concerned that it would negatively impact the value. And then like I would say, cool, I'm doing selfish mining. I'm getting 0.3% more Bitcoin. And my Bitcoin are worth like half as much because everyone's lost confidence because someone's selfish mining. So I actually find that to be generally a sound argument. If you ask me, like why might someone not selfish mine? That seems like a good reason to not selfish mine. So one of the things, this is now finally getting to some of my own work, So this is actually, I don't know how many of you know Miriam. She was a student here. She is now at A16Z, but was a master's student at Columbia. And we showed the following. So it's not all the way down to a third. It's close-ish. So if you have 38.2% of the total hash rate, then there is a deviation with the following properties. So everyone's still tie-breaking against you, so the analysis is as worst case as possible. And everyone else is being honest. You are going to do strictly better with our strategy than being honest. And what's interesting is that each height is still going to have an orphan independently of whatever happened at all previous heights. So the pattern of the orphan blocks is going to look indistinguishable from what it might look like if people just happen to find blocks at the same time. And if you want to, you can play with this probability. You can make it as close to nature as you want. If you want it to be like 1% or 0.01% or whatever, you can do that. The trade-off is just that the lower the orphan rate, the less extra profit you're getting, but you will always get extra profits. You're trading off your extra profit for looking closer to nature. Okay, so I think I have like only a couple minutes left, right? Yeah, okay. So let me say this is the last of the, so I only got to do one model in the end, so I'm glad I put the question marks there. I will just zoom to the end. And I obviously tried to do way too much, which is fine. And, all right, I think I'm almost there. Okay. All right, so I guess I will spend 1 or 2 minutes just describing this cool new attack. So in 2022, this is right before Ethereum switched off of proof of work. So the attack is now moot because Ethereum has a completely different consensus protocol. But before, when they were proof of work, the target of you creating your block, that depended on the timestamp between your block and the previous block. So the difficulty was adjusting per block. So every single block, it was changing. And in particular, the difficulty goes up every 9 seconds. Okay, so every 9 seconds, just to be clear, this is if you set your timestamp to be 9 seconds after the previous block, then your difficulty is higher. If you set the timestamp to be 8 seconds, it is not higher. It doesn't know about physical time. And okay, so when these guys first told me about the protocol, I was like, oh, that's really clever. So it seems like you should just always pretend you're 8 seconds away from the previous block, or at least round down your timestamp so that you don't make anyone suspicious, but you can still save some on the difficulty. And then they told me that actually, that's not what you could do that. There's something better you can do, which is that in Ethereum, because blocks are found every 13 seconds on average, there's actually a lot of conflict. And so they said, and the way that they break ties in favor of the highest difficulty. Is that actually there's so much conflict that it is better for you to increase your own difficulty, make it a little bit harder to find a block, but now you're guaranteed to win any ties. Is that okay? So that was kind of cool. So they presented this, and then they also it was a theoretical paper to describe why the attack is profitable, and they also looked at data from the Ethereum network. And you can see, if you can kind of process something looks funny about this without even knowing what it is. But what this is there's a specific pool, and they charted the timestamp difference between blocks that they created in the previous one. And what you should see is it exponentially decaying. And what you notice is that there's conspicuously missing every multiple of 9. And it seems like it's just been added to 1 second before. And that is exactly what they did. This is the leader of the pool. They immediately said, this is what we did. And you say, I, as a mechanism designer, I'm sort of very thankful that he said, this is basically, people should do more mechanism design. So that sounds great. And anyway, so that's just to point out that it's not selfish mining, but there is detection of something with a very similar flavor. But this is the only case I'm aware of. And I think maybe, should I talk for 2 more minutes or should I just stop? Let me do this. I think I will tentatively stop. And if nobody asks questions, I'll say something else. But Yeah, okay, yeah.
If people use the tie-breaking protocol of taking the later block instead of the earlier one, that makes selfish mining more attractive. What if you have atomic miners? Nobody's got more than 1%, but some group of those miners all agree to use this protocol. Does that cheat?
Yeah, so yes, it would, but let's just go through everything they would have to do. So first you would need a group of at least 32, say at least 33 of them would need to get together. Then what they would need to do is they would need to make sure that when they create blocks, they send them to each other, but they do not broadcast them outside the group. But if you could do that, then you could do this attack and they could find a way to split the profits amongst themselves and
It's
stuff
not
like
enough
that.
just to always take the second block in a tie.
So even if they just take the second block in it, so if they were,
All the cheaters will all have second blocks.
so, let me think through that. So I think actually if you take it also depends on what you mean by second. So if by second you mean the one you heard about second, then I think there's actually something even worse you can do, which is if everyone's going to tie break in favor of the block they heard about more recently, then I would just be like, why am I even going to point to this longest chain? I can just I can override blocks in the past, right? By just by saying that like this is out there, I'm going to ignore this and I'm just going to try and override it by pointing one before. Right, and then if everyone tie breaks in favor of what they heard about more recently, I'll just make it, I'll broadcast it, everyone will be like, oh, I heard about something else more recently. The other thing that's tricky is like if you can also go by timestamp. So one thing that makes selfish mining maybe vulnerable is that the timestamp is going to be older because I found the block first. So you can say, what if I break ties in favor of the later timestamp? That would be bad for selfish mining. But then you have the same problem where sort of like I was like, well, if you're breaking ties in favor of the latest timestamp, then I'm just gonna try to override things in the past. So I think it's tricky. If you ask me to guess, I think that you would need, like if you wanted a mining pool to selfish mine, they would need to run a reasonably tight ship that like it wouldn't be, like you would really need to make sure they don't broadcast the blocks outside of it. If you could convince people to just tie break in favor of you a little bit more often, then selfish mining is more profitable. And so so for example, it's known that if people tie break randomly all the time, then selfish mining is profitable with 25% and no more. So if you can convince more people just to tie break in favor of you, that maybe doesn't require as tight a ship. You can lower the 32.9 a bit. But the conglomerate of miners that need to not share hidden blocks with other people would still need to be pretty large.
So I'm wondering whether there is any evidence of collusion between the selfish miners. So if I know that you have some hidden blocks, and I also have hidden blocks, maybe I could form a coalition with you and we can together coordinate on when we want to release.
Yeah, so so my understanding, so this is getting a little bit outside my expertise, but my understanding is that mining pools tend to both be pretty hostile towards each other. So I think there are other kinds of attacks I didn't discuss because they're not like attacks on the underlying protocol, they're just attacks that target a specific mining pool. My understanding is that those are actually fairly common and that everyone just knows that mining pools do that and they try their best to defend against it. And that's kind of known. My understanding is also that when they're not attacking each other, they do like set up networks to be able to communicate with each other much quicker so that they don't accidentally orphan each other's blocks and stuff like that. So there's like both collusion and the competition, and they're both like very aggressive. Like I think they're both very aggressive, which I don't know if it's weird that both are happening simultaneously, but I think they're both very aggressive in both spots.
Is it possible one reason this has never happened that we know of, the idea that there's no honor among thieves? That the question of if a group of miners who are not a publicly known pool had to collude to do this, then they have to figure out how do they share the proceeds, right? Because only one of them is going to get the block reward for each block.
Yeah.
And that's a problem.
Yeah, so I have not, that's a really good point. So I have not yet thought of what would the game look like among 5 players who together have 35% of the hash rate and can't verify what's like. It could be that depending on how you set up the game, like if like I think it depends on exactly how they communicate. Like I could imagine trying to set it up where I say, you promise me that you have 5% of the hash rate. I better see you producing 5% of the blocks, and they better be pointing where they're supposed to be pointing. And if you produce less than 5% of the blocks, then I'm just gonna, kick you out of the pool or something. On the other hand, like I haven't thought that all the way through, and I'm, hesitant and like.
Ironically, that's a trusted arrangement.
Exactly. Yeah.
Right? Which then, if you're going to participate in that, it begs the question, like, I have 10% of the hash power. I'm just going to mine honestly, create 1 out of 10 blocks. That's a profitable business strategy for me with zero trust assumptions.
Yeah, so I think, so I would say, like, if you ask me to like really think hard about why does it not happen in practice, I would guess that people are just risk averse and there's a lot of uncertainty, and so I think that's one example of uncertainty. So like for example, like if I'm thinking of like doing this as a mining pool, I would be scared that just like people are going to leave my mining pool as soon as they find out that I'm doing this. I definitely can't trick people into helping me selfish mine because they'll know that I'm saying like, hey, please mine on top of this block, even though nobody else has heard of it. For like a conglomerate of miners, I still feel like they should feel uncertain about like, is someone gonna rat them out? Is someone gonna accidentally tell other people and then we're gonna lose our business? And stuff like that. So I feel like maybe risk aversion is probably the main reason for like conglomerates not getting together. And just be like, I'm not predicting conglomerates should get together or something like that or anything, but I would say my like stance is sort of like, I think this is cause for concern in the long term, and I wish people would take it a little bit more seriously, but I don't think it's like an existential threat right now, right?
But doesn't the possibility go down as the hash rate goes up? Because now you have like more and more industrialized mining, right? Like to the extent that like 20-30% of the hash rate is public companies now, they might go to jail. Who knows?
Yeah.
If someone says like, oh, whoever did it, they're gonna get sued and stuff like that. So is it like, I'm just thinking out loud, is it possible it's too late? 10 years
to do
ago,
this specifically. So I think, I mean, that definitely makes sense. Like if, for example, the miners are regulated in the US, like I would imagine that if you were caught selfish mining, you should expect to get slapped with some kind of violation and some kind of fines. And so, how would I put it? I think that, like without trying to say anything that sounds political, I feel like that seems totally plausible to me in practice to the extent that like I'm not a practitioner, but like it's not the way a lot of the discussion always sounds. And so I feel like I like studying kind of like the pure economics. That at least we understand the pure economics, and then whatever people want to do on top of that, if they want to like add regulation, I'm sort of like that's way outside my specialty. It sounds fine to me. Yeah.
All right, let's just finish your time. Thank you.
Sure, but I'm happy to.